Okay, so this video is going to cover some basic differentiation rules, kind of like our limit laws. So in class, we just finished talking about the limit definition of a derivative, and we came to a realization that there was possible some shortcuts in the process. So we're going to talk about those shortcuts today. So in your table of contents, we're talking about the basic differentiation rules. This is standard D1. This is page 39 of your journal. So the target is students will find the derivative by applying basic differentiation rules in order to calculate the instantaneous rate of change at any given value. Remember that the purpose of a derivative is to in fact find that idea of the instantaneous rate, that unique slope formula belonging to that function. Okay, so let's talk about some notation really quickly before we dive in. This is something you might want to put on a post-it note on the side of your notes in a different color possibly, okay? So we've been using, let me get a pen, sorry. So we've been using f prime of x. Remember, we read it as f prime of x. This is derivative notation when we're in function form. What it means is we're taking the derivative of f with respect to x, x being our independent variable. So this notation shows us our independent variable here, which we're used to seeing. This is common function notation. So we know that our independent variable is there, but in our derivative rules, knowing our independent variable is really, really important, independent versus dependent. So our f is our dependent, our x is our independent. Okay, sorry, I just need a little thinner pen. Okay, if we're in, remember this is if we're in function form. So that leads to f prime. If we're in just basic y form, we use dy dx. Now that notation, if we think about what it is we're doing when we're finding the instantaneous rate of change, that idea of change in y, don't write this down, change in x, we kind of read that as delta y over delta x, which makes sense why we're using a d here. So again, this tells us that our independent variable is here. And our, sorry, opposite of that, ignore that. Y is not our independent in this situation. This gives us our dependent. And our x, of course, is our independent. Okay, so especially for those of you that are in physics C, you guys have been dealing with things like dy dt. And what that tells us is we're taking the derivative of the y function with respect to the t variable. T being our independent, y being our dependent. Okay, so as problems change, so are our notation, and it's always going to match the form that we're in. That's a really important thing in here. Getting used to that notation kind of helps you along in the process of what to do when. Okay, so that's not what I want to do. So that right there gives us our derivative notation. I do not know how to spell today. And of course, y form. Okay. We want to always be able to distinguish between our y and our derivative, f and our derivative, so that notation is pretty important. And you know that's one of my big things in here. Okay, so derivative and notation in y form. Okay, then we have things like the operation of the derivative. So this idea of d derivative with respect to x, and then we have something behind it. Okay, so this is our function, okay, whatever this is. And what this means, this is our operation to find the derivative. This means find the derivative of whatever's in our brackets there. Okay, so just a couple things to kind of get you into the hang of when we write that mathematics, what that mathematics means, using that proper notation in the proper setting. Okay, so let's kind of get down to the laws now. So, excuse me, the constant rule, if we're taking the derivative of any constant value, like the derivative of 5, derivative of 9, derivative of 12, that derivative will always yield a 0. Okay, and the reason for that, if we think about the graph of a constant function, so let's say at C, we get this horizontal line through that particular y value. And if we think about that and the slope, because that's what our derivative is finding the slope, we get that our slope, of course, is equal to 0, which makes sense why our constants go to 0 in a derivative process. Then we have the basic power rule, and the power rule says to take our exponent, multiply it in front, and take our variable and raise it to the power minus 1. So we're subtracting, we're first multiplying, and then we're subtracting 1 from our exponent. Now if there's a constant in front, that's kind of the constant, constant multiple rule. We kind of put the power rule and the constant rule together because it's just easier to just do it. It makes sense. But really, in reality, what we're doing is we're taking that constant, that coefficient that really doesn't do anything, that just comes along with our process until we actually need it, and we're multiplying it by that exponent, and then, of course, taking that exponent and subtracting 1 from our variable, or from our exponent value. And then the sum and difference rule says that we can take the derivative of each term independently. So we can take the derivative of the first term, so the first function, whatever that is, and keep that addition or subtraction in place, and of course, g prime. So very much like our limit laws, these are kind of natural things we do when we know our derivative process, but this allows us to say, yes, I can do that. Okay, so let's do a couple of examples at the bottom. A lot of times when we're doing these derivative rules, there are a lot of times where we're going to have to rewrite our function to get it into the power form that we talked about in class that allows us to use these rules above. Okay, so a lot of times we're taking some time up front to rewrite. Remember, when we rewrite, we're not really taking the derivative yet. Okay, so we're not finding f prime yet, so we don't want to do that. We're just really simply taking our f and we're putting it into a form that we want. Now, we know that to be in power form, our x term needs to be in our numerator. So we can use our power rules to manipulate our functions to get them in the form that we need. So I know that one of the power rules says that if we have in the denominator, if I want to change the position of my x term raised to some exponent, I can just simply negate the exponent value. Okay, and what I mean by negate, I mean to change it to the opposite sign. Changing an exponent to the opposite sign changes its location. And then the second term, I really don't need to do anything. So I'm going to bring down that second term. I don't want to take the chance of taking the derivative of that second term yet. So if I'm not in my derivative process, I'm just going to bring down anything that I don't need to rewrite. Now that it's in that power form that we talked about in class, now I can easily take the derivative. And the rule says all we have to do is to take our exponent, multiply it by the coefficient, that's that constant multiple rule, so 4x, and then subtract 1 from the exponent. So -2 minus 1 gives us -3. Same thing, I'm going to keep the minus sign, that's our sum and difference rule. Take our exponent, again constant multiple, and multiply it by front, so 12, x subtract 1 becomes x squared. Now I always want to put my equation back in the form it was. So I don't want to leave things like negative exponents, like rational exponents, things like that, because remember these functions are used to calculate slope. And it's hard to calculate when we have negative exponents and rational exponents. So we always kind of want to take care of that. So again, I'm just going to rewrite. The 4 numbers do not move. They stay where they're at. So that 4 is in my numerator right now, so it's going to stay in my numerator. But to change the sign of my exponent, I change its location. So back to the denominator. Minus, and then that 12x squared is fine, so we're just going to bring it down. Okay, so a lot of times we're taking time to rewrite up front, doing our process, then rewriting it at the end. Okay. The next example here, I can do one of two things. I can separate it, but this is easily factorable. I can factor out an x, cancel it out, and it's going to cancel out that x that's in my denominator. So that's a simple thing to do. So again, I'm going to rewrite. I'm not taking my derivative yet. I'm going to factor out what I need to cancel out in my denominator, which is a simple x. So I get 3x cubed minus 3x squared minus 2 over x. And because of that, now we can cancel out that x. Remember, we're not really canceling out, we're dividing it out, so it's becoming 1. So really I have 3x cubed minus 3x squared minus 2. And now it's all in that form that I want so that I can easily take the derivative. So now my notation shows that I'm taking my derivative. First term, that constant multiple rule, so 3 times 3 gives us 9, x, and I'm going to subtract 1, minus, we're keeping the operation, 2 times 3 gives us 6, x, when I subtract 1, I get 1, and then the constant rule says that negative 2 is going to 0. So really, this is all I have. Sorry, my exponent is not negative there. Let me rewrite that. Got a little fuzzy. So 9x squared minus 6x. Okay, and that, I don't have any negative exponents, I don't have any rational exponents, so therefore I can just leave it and I'm done. Okay. Next problem at the bottom. So the next one is a product. At the top, we do not have a product rule. Therefore, I can't just take the derivative of each term independently. I have to get into the form that allows me to use the rules at the top. So simple thing for this one is just to simply distribute it out. So that's exactly what I'm going to do. Again, I'm not taking the derivative, so I'm just going to bring it down, and I'm just going to distribute out x squared plus 2x plus 3x plus 6. Simplifying, combining my like terms. I get that. Okay, so now everything's in that power form, so now I can take the derivative. So here's my derivative notation. Okay, that first one is just the power rule. We're bringing that power to the front, and we're going to subtract 1 and get a first power. Plus, that really is a 1. If there's no exponent there, like in front of a coefficient, that exponent is 1. So 1 times 5 gives us 5. X, when we subtract, we get 0. And then that 6 for our constant rule goes to 0. Okay, so I'm just going to rewrite it real quick. So that 2x, I don't really need that 1 there. And then if we think about x to the 0 power, anything to the 0 power, it gives us a result of 1. Of course, with the exception of 0 itself. Okay, so then plus 5, and then we're done. Yeah. And then the next one. So the problem at the top, this problem right here, I was able to factor out and cancel out. The problem with this one is I'm not going to be able to factor out. The most I'm going to be able to factor out is an x squared, so that's not going to cancel out my denominator. So another good strategy to use is a separation strategy. Sorry. So I can separate it into 2 separate fractions. So kind of going the opposite of where we usually go when we combine our, we get a common denominator to combine our fractions. Okay. So if I'm doing that, then I can use my exponent rules. My exponent rules say that anytime that I'm dividing, all I have to do is subtract my exponents. So x, and then 3 minus 5 gives us a negative 2, minus 5, x, and then 2 minus 5 gives us a negative 3. And now they're in power form, so I can take my derivative. Okay. Constant rule, or sorry, power rule says to bring that power in front and subtract 1, so negative 2 minus 1 gives us negative 3, minus, Negative 3 times 5 gives us a negative 15, which is going to change that to a plus. And when I subtract 1, I get a negative 4. So again, I don't want to leave negative exponents in my problem, so I'm going to take one additional step and rewrite. Numbers stay where they're at, so they're in the numerator, they stay in the numerator. Variables move down. That's that x to the third. Plus 15 stays, x to the fourth moves. And then we get an equation that doesn't have any negative exponents, and we kind of want to leave it like that. Okay. So there's a lot of manipulation that we do beforehand and after to kind of simplify our answers. And that's a good practice to have that helps you with your algebraic skills. It's going to help you because on your AP exam, all of your answer choices are usually simplified. Okay, so it's good to just know how to do that. Okay, and the last example at the bottom. So that last example at the bottom, let me roll that up. Okay, that last example right there, so it says that what values of x? So think about what we're trying to find. We're trying to find some x values, and that's an important thing. So what values of x? Will the function f of x equals x cubed minus 2x have an instantaneous rate of change of 4? Remember that idea of instantaneous rate of change, that's our slope. So what we're talking about is in fact that our slope, our f prime, is 4. So our f prime is equal to 4 here. Sorry, I had to change out my pen because it's not working anymore. So I'm going to have some serial killer writing right here. Okay. So first thing I want to do is, of course, take the derivative because our derivative gives us our slope formula. So we need that first. So I'm going to take the derivative. So f prime of x equals, I get 3x squared minus 2. Then the next thing we're going to do is to plug in. If we're looking for f prime, we're plugging into x, but here we have f prime, and what we're doing is trying to solve for x. So I'm just going to plug in everything where it goes. So 4 equals 3x squared minus 2. I'm just going to solve out for x. So of course, adding 2 to the other side gives us 6 equals 3x squared. So there should be equal sign. Divided by 3 gives us 2 equals x squared. Taking the square root of both sides gives us that the square root of 2 is equal to positive and negative x. Remember that positive and negative is not part of the square root, it's actually part of x. But when we solve, that's what transfers it to the square root. So then we get that x, anytime x is positive square root of 2 or negative square root of 2, we're going to get a rate of change of 4. Okay, so we're going to stop there. The last thing I want to do though is I want to go on to the next page because we're in class, we're going to prove the derivative of sine and cosine. There's a couple things that we need to know first. Like we need to know some identities because that idea of f of x plus h. So we're going to use our addition identities for cosine and sine. So I kind of just want to get them up here. So if we think about the cosine of a plus b, one of our identities said that the cosine of a plus b gave us the cosine. Okay. Actually, you know what? We will do this in class together because my pen is not working. It's going to look all craziness here. Okay, so we'll start in class with these two identities tomorrow. Okay, so if you have any questions, come in and see me.